So this is one of the Cohere Lab sessions, and we are going to be having a very interesting talk today from Diana, who's on the call, with one of the most recent interesting publications, at least to me, because it's been able to reshape the way I think about some of the research that I've been looking at, and that's to do with one tokenizer to rule them all. And maybe Diana, you could just go ahead and introduce yourself, and we could get started right away.
Yeah, sounds good. Hi, my name is Diana. I am a research scholar in the 2025 cohort at Cohere Labs. Some of you may have seen me from the info session or stuff like that. But yeah, really happy to discuss my research and hear some of your thoughts and questions as well.
That's great. I am aware that we do have, I believe I did see Ahmad on the call as well, actually. So this is actually a joint call, and I think this might be the first of its kind. He might actually correct me, but this is basically two communities working together to bring this together. So this is the Regional Africa community and the Regional Asia community. So maybe Ahmad could actually go ahead and introduce himself as well, and then we could just go right into it.
Hi, Bronson. Thank you for introducing me. And I am regional lead for Geo-Regional Asia, and very excited for this session by Diana. Thank you so much. And I'll let you continue.
Yeah, I'm really excited to be here. Multilingual NLP is like one of my top interests, and I'm really happy to like be in this space hosted by both groups. So I hope that we can bring in unique perspectives on both sides. Should I start with my slides?
Yeah, sure thing, please.
Okay, cool. So as Bakunga said, the name of my paper was One Tokenizer to Rule Them All, Emergent Language Plasticity via Multilingual Tokenizers. And I'm going to start off with a little bit of motivation first. I think all of us are very familiar in these two groups that LLMs are severely limited by their language support. Here I have some of the most common open source LLMs and what their claimed language support is. What are their listed languages that they claim to support for these various models? And for a lot of them, it's extremely low. So Llama, Mistral are like almost in single digits. Aya is very exceptional in that we had 101 languages, and I'm sure many people here were involved with that. I was as well. It was a great effort, but it's still really far away from the total number of languages that are spoken in the world. This is estimated to be around 7,000. So what can speakers of a given language do? Pre-training is very expensive, and so it's not accessible to the majority of people, especially speakers of lower resource languages who are more likely to have a disparity in terms of resource availability and the sheer amount of money and compute it takes to train these models. This plot is looking over time for some of the largest models and what the training cost was. And you can see from 2023 onward, which is like, with the field changing so fast, these are really the only models that we're talking about right now. And training is in the 50 million to 100 millions. And this is just not something that's accessible to people. So what do you do if you want language support? You have to adapt a base model. And this is a very common approach that many people in communities take. So we're approaching this question of like, what relatively cheap interventions can we make early on in the training process, maybe even before pre-training starts, that would set up the model best for language adaptation after pre-training, potentially reducing costs and making it easier to adapt to new languages. In particular, can we use a tokenizer that's trained on more languages than just the pre-training target in order to improve language plasticity, which is this quality of being able to quickly and nimbly adapt to new languages with a lower amount of data and compute? And at the same time, it's really important for us to preserve pre-training performance while imbuing the model with these capabilities in language plasticity. Going towards tokenization a little bit, when a tokenizer is not trained on a given language, the sequence lengths can be really long. So here, this is a sample from Flores 200, and we have the same sentence in Hindi and in English. And each block of color corresponds to a token. This is using the GPT-2 tokenizer. And you can see the sequence is much longer for the Hindi side, the tokenized sequence, as compared to the English side, even though the number of characters in the English side actually appears to be longer. But the tokenized sequence really is blowing out of the water here. And the GPT-2 tokenizer was trained on English only. So it hasn't seen the Hindi script before Devanagari. Why does this happen? There's a quality called byte fallback, which is present in BPE. That's byte pair encoding, the most common tokenization algorithm right now. And in general, pretty much all of these models are using some form of byte fallback, and that means that we're not seeing UNC tokens anymore. If a letter from the Devanagari alphabet wasn't seen in the tokenizer training, it's not encoded as an UNC. These question marks are just not properly rendered on the screen. But you can see 0% characters mapped to the UNC token. What actually happens is that these characters are decomposed into bytes. So here you can see, first we have characters from given alphabets. So you have A, you have the Greek omega, and etc. And then you have the UTF-8 encoding. So what is one letter in English is represented, or in the Latin alphabet rather, is represented with 1 byte, but a character from the Chinese alphabet, or Chinese writing system rather, is represented with 3 bytes. And this can go up even to 5, depending on what writing system we're talking about, if there are diacritics, stuff like that. So you can imagine, if everything is being decomposed into bytes, the length of the sequence really just explodes out of the water. This is most egregious when the script is not present in the tokenizer training, but in general, if a language is not present within the tokenizer training, even if it shares the same script, compression won't be optimal on that language. And what does that mean? That means that we're having really long sequence lengths, longer than they need to be. And that means training is going to take longer if you're using the same amount of data. If you're constraining by the number of tokens seen that instead, then less valuable information is going to be seen in training. So you can imagine that the performance of the model on that language would suffer. Kind of going along with that, the effective context window is smaller for that language because there's less information contained in the same amount of tokens. And then after training, you're going to see longer inference time, so it's much less efficient. And also when you're talking about using like ChatGPT or something like that, any model hosted on a public API where they charge per token, which is the standard, you're going to see higher API costs for speakers of lower resource languages. So there's this gulf in terms of how speakers of different languages are treated. And we want to set up our models to be better adaptable after pre-training. So I'm going to go into our experimental setup now. We're training 2 different tokenizer variants. So one we call the cluster tokenizer, which is trained on only the pre-training target languages. And those languages we call the primary languages. I'll go into this distinction on the next slide. But we train 3 different cluster tokenizers and models. We have the European cluster, Middle Eastern Indic, and Asian. So I'll show those later as well. But for more details, you can check the paper. And then for all of the clusters, we have a universal tokenizer, which includes not only the focus languages or the primary languages, but also all of the expanded languages, which will be part of the set that we're doing adaptation on. And yeah, just to go into this like primary expanded language distinction, this is new terminology in our paper, but it's introduced in order to explain a valuable phenomenon. So a lot of these models, they claim to support many languages, but only list a few of them by name and only show evals for a few of those. So to take the example of Mistral Large 2, on the release for the models, they only list French, German, Spanish, etc. And if you check out the source, you'll see that they report evals for those languages. They also claim to support dozens of languages. Those dozens are not listed, but those languages were seen during pre-training. In addition to all of this, we also have the, thousands and thousands of languages throughout the world that were not seen in pre-training and are not claimed to be supported by the model. But you're not quite sure if a language has been seen during pre-training or not because of the way that they choose to disseminate this information. And in general, all of the large models, they have been quite cagey with this information, not listing all of the languages that the tokenizer was trained on or the model itself. And so we're trying to do the work of uncovering what would equip the model best for adaptation down the line in a variety of different setups. So yeah, in all of the adaptation experiments, we're going to take a pre-trained model, which was trained with either the cluster or the universal tokenizer. And then one potential way of doing language adaptation is continued pre-training. So if you have a large amount of different data, let's say in the primary languages, in the expanded languages, which you're trying to improve the model's performance on, and some miscellaneous large collection of data, which we call the cooldown mix here, then you can do continued pre-training. Another very standard approach is supervised fine-tuning, which is targeted adaptation to the expanded languages. So you don't have any other data except for the languages that you're trying to expand coverage to. The third scenario we're looking at is if you're expanding to a language that was not present in the tokenizer training or the model pre-training. So this is the most difficult setup with a low amount of data and this targeted adaptation to one language at a time. So we'll go into some of the results now. In continued pre-training, you can see that the universal tokenizer leads to significantly better adaptation in the expanded languages. So the expanded languages are on the in the white part of the plot for each one of these clusters, and we're comparing win rates against a model trained with the cluster tokenizer, which doesn't include the expanded languages, versus the universal tokenizer, which is the star. So you can see we're seeing win rates of around 20% gains here, which is really quite significant. And in the blue part of the chart, you can see the primary languages. So to make this a little more clear for the European cluster, right? The primary languages include German, Greek, the languages that the model was trained on specifically to support, right? And then you have the expanded languages, which we're trying to adapt to. So for the European cluster, we have Arabic, Hindi, Japanese, etc., right? So for the primary languages, performance is around the same. There's a little bit of noise in those data points, but in general, you can see that the performance is, there's very little impact on the primary languages when you include a lot of languages in your tokenizer training, so using the universal tokenizer. And yeah, sorry, these are around 20% win rate gains on average. In supervised fine-tuning, you can also see significant improvement. So this is when we're only training on the expanded language data in fine-tuning. And on average, there's 8% win rate gain when you're using the universal tokenizer. So in both cases, regardless of what adaptation strategy you choose, depending on data availability, using a tokenizer that supports more languages enables better adaptation. And then in the most difficult setting, these are extremely low resource languages, and the data was not present in the pre-training at all. And I'm saying it's low resource because we used a very small amount of data points for the supervised fine tuning. Even in this case, the model trained with the universal tokenizer performs significantly better. We're seeing 5% higher win rates, up to 5%. And in this setting, like those 5% really mean a lot. I'm sure like many of us are familiar with that. So yeah, this is definitely a great choice. Now I'm going to go into some sort of auxiliary results. So outside of the main setup of language adaptations, you may ask, why not adapt the tokenizer after pre-training? So if you train using the cluster tokenizer, why not adapt the vocabulary of the model's tokenizer after the pre-training stage? This isn't nearly as effective as training with that tokenizer from the start. And you can kind of imagine why. But in this experiment, we took the model that was trained with the cluster tokenizer and then substituted in the universal tokenizer. So tokens that were shared between those two tokenizers use the same embeddings from before. But then the new tokens, which represent the expanded languages, those tokens were either randomly initialized or initialized with the mean of the other shared embeddings. So random, we don't even need to talk about, that's not competitive. But if you initialize with the mean of the shared embeddings, you definitely perform much better than using an unadapted tokenizer, right? So comparing to the performance of the cluster tokenizer, win rate 17% versus 30%, it's a huge improvement. But if you train with the universal tokenizer from the start, win rate is 7% higher. So this really goes to show that improved compression, it has a huge impact during pre-training. So I didn't go into too much detail about our data mix. I'm happy to share that information, but the most important part here is that we included a small percentage of the expanded languages in the pre-training as well. So for example, for the European token, the model trained with the European tokenizer, right? Actually, let me rephrase that. The European model, right? So it's trained primarily on the European cluster languages. We still include the other languages, so from Asian, Middle Eastern, Indic, etc. We include that at a small percentage, at 5%, for the results that I've shown you so far. And this is to avoid undertrained tokens, which can really impact performance. So what we wanted to do is determine if that 5% is what's enabling the model trained with the universal tokenizer to perform better than the model trained with the cluster tokenizer. So we varied this percentage down to 0. And you can see even at 0%, the win rates on expanded languages are better. So even if the expanded language data was not present at all in pre-training, having better compression in the tokenizer, having those languages supported in the tokenizer enables significantly better adaptation. We're seeing up to 12%. So these results hold even if that language data wasn't present in pre-training at all. And there's no performance impact on the primary languages, which you can see on the left side as well. Now we're also taking a look at the vocabulary size. So there's been a number of papers that show that in general, a lot of models have been using a lower vocabulary size than is optimal. 250K is a little bit on the larger end, but it's what was used by Gemma. It's becoming more and more the standard because these language models do really require a large vocabulary size in order to adequately represent the text. So we were using 250K vocabulary size in all of the experiments up until this point, but we decided to ablate that as well. And you can see that the performance using the universal tokenizer does suffer if you take the vocabulary size down to 100K. And this is performance on the primary pre-training languages because, as I said before, it's really important for us to preserve performance on those languages as well. And when you bring that down to 100K, there is a significant difference in primary pre-training languages. when you're using the universal tokenizer. The cluster tokenizer is still fine because you're representing a smaller amount of languages in the same vocabulary size, right? But with the universal one, with so many diverse scripts and languages, a large vocabulary size is even more important. But as I said, this is still like relatively standard. Here I go into some more detail about how we did the tokenizer training. We didn't just evenly weight all of the languages in the tokenizer training, or as I've said before, like a lot of these models don't release information on how they train their tokenizer or any other specific training details. But another common approach would be to take the natural data distribution, in which case lower resource languages will be extremely lower weighted, or to take that distribution and upweight the lower resource languages. I believe the Gemma tokenizer, they upweighted those a little bit. So what we do here to compare our custom weighting is just to compare with the uniform weighting, which means that each language is weighted the same, which is even more charitable to low resource languages than taking the natural data distribution, which is what is most commonly done. So what do we propose instead? The way that the weight for a language is determined is by taking the proportion of the data size, so that's this W subscript D, and balance it with a language bucketing scheme. So the language buckets are determined by language family and script. So the intuition here is that languages with the same script are more likely to share tokens, and then languages within the same language family are even more likely to share tokens, right? So we use those two factors together, and that weight is intended to increase the representation of low resource languages, especially ones with one-off scripts that aren't shared by other languages. We want to make sure that they're still adequately represented in the tokenizer training, but we don't want to deviate too far from the distribution of the training data of the model, because then our compression will be suboptimal. That's why we include the data size factor in the first place. So that's what this formula basically shows. We're trying to balance those two factors, and we normalize as well to make sure that all of them sum to one. So comparing our weighting scheme against now the uniform, coming back to that, in pre-training performance, you can see that, especially for lower resource languages, our universal tokenizer performs better than if you have just the uniform tokenizer, which is again more charitable than just the natural data distribution. And here we're looking at the compression ratio. So we talked about a few reasons why having longer sequence length is suboptimal for lower resource languages, but in general, there is a correlation between the performance of a model and the compression ratio. There are a few papers on this topic, but even showing in our own results here, this plot is win rate versus compression ratio, and you can see that there's definitely an inverse relationship. So the higher the compression ratio, meaning the worse the compression, the lower your win rates are. And you can see here a comparison between the primary languages, or sorry, yeah, between the primary languages and the expanded languages for both the universal and cluster tokenizers. And for the cluster tokenizer, where the expanded languages are not represented at all, compression ratios are really bad, even over 3. In general, you want your compression ratio to be below 1, which means that the tokenizer that you're comparing to has worse compression than your tokenizer. And with the universal tokenizer, we see all of our languages are at around 1 or below 1 compression ratio, and this is both the primary and expanded languages. And there's certainly a relationship here with win rate and compression ratio. So that's kind of a little bit of intuition also as to like directly impact of including more languages in your pre-training. and what the impact is on the downstream performance. So TLDR, train your tokenizer for more languages sooner rather than later. This sets up your model for better language adaptation and post-training, while preserving performance on the primary pre-training languages. And here you can see a comparison of a training run with the cluster and universal tokenizers. And when you use the universal tokenizer, you see 8 times faster adaptation. So in 1/8 of the data, you can achieve the same performance as you do with the cluster tokenizer. And you also get 2 times better performance, which we dub like plasticity. So it is much more data efficient, and you'll get better performance on your expanded languages. So yeah, that's the end of my slides. I'll be very happy to take any questions. I know there was a lot of detail there.
I think that was really good. I was kind of following along with the paper as well on the side, and I think there's just so much. Like if you haven't checked out the paper, please do. And we can actually get into some questions. I actually also have a few of my own, but definitely open to seeing how the floor reacts first. Does anyone want to go first?